Thanks everyone for attending my presentation. I'm really happy to talk about some of the work that I've been doing in Scala over the past couple of years. The flow of the talk, I'm going to talk a little bit of the history of the project, and we're going to talk about something called regular type expressions, which I'll show pretty much by example. There are 5 theoretically interesting challenges in this project. And of course, theoretically interesting is very subjective, but at least these are things that were interesting to me and challenging in developing the project. And we'll finish up with some final thoughts. So first, a little bit of history of the project. So in 2016 at the European Lisp Symposium, I presented this concept that I called regular type expressions. And it was implemented only in Common Lisp, and there's a publication there. And I went on to do a PhD thesis on the same topic. And one of the pieces of feedback in the from the jury was that you should generalize this to other languages, not just to Common Lisp. So over the past several years, I've done an implementation in Scala and Clojure, Python, and Common Lisp, and those are all available on GitHub, as you see there. And I just found out a few days ago that a paper on this topic was accepted at the Practical Aspects of Declarative Languages PADL conference in January 2005. So more or less the technical details of what I'm going to talk about here today in very high level. So what is the goal? The goal is we want to be able to efficiently recognize regular patterns in mixed type sequences. And in Scala, these represent as sequence of any. So I want to talk about what this is by example. So in this sequence that we see here, there's some pattern hidden there, and the pattern is in the mind, particularly of the programmer. But if you look at it, you see that there's integers followed by some floats, integer followed by some floats, and the floats might be double precision or single precision. And it's not clear whether at least one float is required or whether the whole sequence has to repeat a certain number of times. And this is the type of repeating pattern and optionality that regular expressions are very good at. So if we look at string-based regular expressions, for example, the string that's highlighted here, IDD, IFDF, ID, so we can use a string regular expression as we see in this surface syntax with the parentheses and the vertical bar to represent or, the plus to represent something occurs 1 or more times, the star meaning that it occurs 0 or more times. What that string represents is some expression which has an abstract syntax tree of a star operator over some concatenation operator, and we're concatenating a literal with a plus operator of a disjunction of some literals. So we want to somehow represent the same thing in Scala with not regard to literal characters, but more general in terms of types. So the first challenge that we have is how do we represent this surface syntax in Scala and in a way which makes it easy for us programmatically to manipulate the abstract syntax tree, the AST. So a regular expression, normal regular expression or regular type expression serves as a predicate for a pattern. So given a sequence, in this case, of characters of mixed types, we want to know whether that sequence matches the regular expression or not. The set of all sequences that match the regular expression we call the language of the regular expression. So we have the regular expression here shown in green, and typically what we want to do is construct a finite automaton which corresponds to the regular expression, and then we refer again to the language of the finite automaton, in other words, the set of all sequences which are recognized by that finite automaton. So the second challenge here is how do we construct such a finite automaton from a regular type expression? So what do we mean by does it match, and how do we compute whether the sequence matches given the finite automaton? So we start in state 0. We look at the first inhabitant of the sequence, first element of the sequence. It's a 13, which is a type integer. And we have a transition labeled int, so we can follow to state 1. And then we find a double, so we can go to state 2, following the transition labeled double. We have another double, then we have an integer, and then we have a string. At this point, you notice that from state 1, we have a choice of double or string. If we had any other type of object, we would stop immediately and say that, for example, if we had a Boolean is not double and it's not string, so we would stop and say the sequence does not match. But we continue as long as we have valid transitions corresponding to the types of the elements. And finally, we get to the end of the sequence and we find the sequence is ended, and we've ended in a state with the double circle there, which means this is an accepting state. So the sequence does match the regular expression. If we ended in a state such as state 1 or state 0, that will be a non-accepting state, and then we would reject the sequence and say that it does not match. One thing that you may have noticed is we did the membership test by traversing the sequence exactly once. So the complexity of this decision procedure is linear. It is in no way related to the complexity of the regular expression. It's only a function of the length of the sequence. And this is because the finite automaton is deterministic. To explain what determinism means, I'll show an example of a state machine which is not deterministic. At this point, if we're looking at the object 3 in the sequence and we're in state 1, well, 3 is an integer, but 3 is also a number. So we don't know whether to take the transition labeled int or take the transition labeled number. If we take the transition labeled int, and then we find the next element of the sequence is 5.6 as a float, we find that there's no transition from state 2 labeled with, and then take the second transition number and find that the next element of the sequence is indeed a float. Unfortunately, this backtracking takes the complexity of the operation from linear to exponential. So we really want to avoid having to backtrack. What we can do is we can modify the state machine such that we don't have this non-deterministic behavior. If we notice that int actually is a subtype of number, so we can relabel the transitions int and number and not int, and then the element 3 is an integer, but it's not a number and not integer. So then the transition, as shown here from 1 to 2, can be taken, and then we find that the next element of the sequence is a float, and so the sequence matches. The third challenge that we face is how do we represent types such as int and not number in Scala? I'm implementing this in Scala 2. I have some hopes of converting it to Scala 3. Scala 3 does have a way of representing intersection types, but as I understand, it certainly doesn't have a way of representing complement types. So we need a solution for that. The fourth challenge is, well, given a set of types, such as int and number in the figure, or in general, some set of types, string, int, number, how do we partition those into a set of types that are disjoint, but such that the union is maintained? So the union of string, int, and number and not int is the same as the union of string, int, and number. So how do we do this type decomposition? And then the final challenge there is, once we have a set of types which are disjoint, and we want to, at runtime, check whether an object is a member of each of the types, we want to decide which of the transitions to traverse. If we check an object and find out that it's not an integer, then we need to next check if it's a number and not int. But we've already checked that it's not an integer. So we have a type check there, and it turns out that we can eliminate those in a straightforward way. So we have five challenges: representing the RTE in Scala, constructing the finite automaton. We have to somehow represent a type lattice, so represent unions, intersections, and complements of types. We need a type partitioning algorithm, and then we need to sort of undo the type partitioning at runtime in order to avoid the redundant type checks. Let's look first at the representation of the RTE. So we need a surface syntax which is declarative, expressive, and composable, and we need to be able to manipulate it at runtime, or it needs to be reflective. Obviously, we need to be able to ask it what type of object it is. This is not a big deal in Scala. We can represent ASTs in Scala using algebraic data types. So we have here I, F, and D as variables which are type RTE, and the type of RTE there are atomic wrappers around built-in types using the class of syntax. And then we can combine those here on line 5 as integer concatenated with the disjunction of D and F, and that repeated or that occurring 1 or more times, and then that occurring 0 or more times. The leaf nodes correspond to the interfaces to the Scala type system, and then the internal nodes of the tree correspond to the operations between those other nodes. The ADT, I call it a quasi-ADT, and I'm happy to answer questions about what's quasi about it at the end of the talk. But we have on the left-hand side the combinational operators, which represent regular expression operations, and on the right-hand side we have the sigma empty set and empty sequence, which are sort of identity operators for the regular expression algebra, and then an interface to the Scala type system, which I called simple type D, simple type designator. More about that later. The second challenge is, given such an RTE as an AST, how do we build a finite automaton from that? And there are well-known methods for doing this for normal regular expressions. We just have to adopt those in a correct way to handle these type expressions. And the most important, or the most interesting challenge of this is how to handle or how to enforce determinism. So I want to show this as a demo rather than trying to actually explain how finite automata are created in Scala using this package. And as an example, I want to start with a piece of data, a sequence of any. And so we have the sequence, which is delimited by these M's and C's, where M means measurements. So M is followed by 0 or more measurements, which are either double or single floats. And then C's are counts, so they're followed by a count, which are necessarily integers. And I can have as many M's and C clauses as I like, but they have to be followed by the correct type of data. So C's are followed by integers, and M's are followed by floats and doubles. I declare this, well, for the demo, I've declared it in small pieces. So a variable I, which represents integers, df, which represents floats or doubles. I have a predicate positive, which takes any value and returns true if it's an integer and positive, a double and positive, or a float and positive, and returns false in all other cases. And then I declare a type called pos, which is the set of objects for which the positive predicate returns true. And I can combine that with the AND operator with integer, and I have the type of positive integers. M and C are the singleton types of the type just containing the string M or the string C. Then I can define the M clauses as M concatenated with 1 or more DFs, so doubles or floats, and the C clause, which is C concatenated with 1 or more positive integers. Then finally, I declare the pattern 1, which is an M clause or C clause, repeated 1 or more times. And then for the sake of the demo, a second pattern, which is slightly different, but may not be obvious looking at it the first time how it's different. So an M followed by 1 or more D or Fs, and a C followed by 1 or more integers. And each of those patterns then are appended with a dot star, which means the pattern itself can occur 0 or more times. So the thing I want to do is ask whether the sequence data at the top matches the pattern. So the language of the pattern contains a set, a theoretical set of infinite size of finite sequences, and we want to know, is data an element of either or both of those sequences? So if I run this demo now, then I ask the question now whether data is contained in pattern 1 or the language of pattern 1. I see that, yes, it is. Data contains true. I can make that text a little bit larger, I think. And then similarly, data is also contained in pattern 2. So from this very small experiment, it looks like pattern 1 and pattern 2 are the same, represent the same language, but we know that's not true because we used slightly different expressions. So how do we examine what is the difference between these two patterns? Which sequences would match one and not the other? So one thing I can do is I can actually look at the finite automaton of the first pattern, and we see that the sequence would start at state 0, and then we can have M's or C's, and if we take a C, then we go into a loop of C's and positive integers. If we take an M, we go into a loop of N's and doubles or floats, and sometimes we can pop between these two different clauses, and if we end up in a final state which has a double circle, then we accept the sequence. If we look at the second pattern, so we see that that's quite a similar finite automaton, still M's and C's, but there's a slight difference that in some of the transitions where you have integers in one and the other, you have a more restricted transition of integers and positives. So we see that the patterns don't actually represent the same language exactly. We might ask, well, what is the difference between the patterns? So we can construct the exclusive OR of the patterns. So now this is a pattern, and if you actually try to look at it, you see the pattern XOR. The printed representation that is quite long, so it's certainly not something that a human being wants to construct by hand, but we can convert that to a finite automaton and then view that graphically. And I've noticed in the debugger, this seems to be extremely slow. I think the debugger is probably doing a lot of stuff that perhaps I don't care about. This is the finite automaton of the exclusive OR. So this represents all of the sequences which match pattern 1 but not pattern 2, or match pattern 2 but not pattern 1. So any sequence which would traverse from state 0 to some final state, 4 or 9, would be in that XOR language. And so something like traversing to 3 into 6 into 2 into 5 into 2 into 5 into 2 into 5 into 2 and then to 4 would be such a sequence that would be in pattern 1 and not 2, or in pattern 2 but not 1. But what might be a cleverer thing to do is find, well, what is the shortest path from 0 to 4? So that's exactly what we can do here. We can find a spanning trace. So in this case, a Dijkstra algorithm is used to find the shortest path from the starting state to any final state. And then if I have this set of types, I can ask, well, can I actually generate a witness, a sequence which obeys those types? So the spanning types is, here we have some satisfiable. So some means that, yes, it did find a path. The path contains only satisfiable types. We'll see in a few minutes that some types are unsatisfiable, and some types we don't know whether they're satisfiable or not. And then we have a list of, well, there's C as a string and an integer which is not positive. Such a sequence would be in this exclusive OR language. And then we can actually print, well, what is such a sequence? Well, the sequence that has C and 0 would satisfy that. Another slight thing you might want to do is find out or ask the question, are all strings that match pattern 1 in the set of strings which match pattern 2? In other words, is pattern 1 a subset of pattern 2? So we can generate the finite automaton representing pattern 1 and not pattern 2. And if pattern 1 is a subset of pattern 2, this will be empty. So if I display that, then we have a finite automaton that represents this intersection. And is there a path from 0 to a final state? Well, no, because there's no final state. So in this case, we know that pattern 1 is not a subset of pattern 2. Okay, so the third challenge now is how do we represent types like integer and not number, which have intersections, unions, and complements. So basically, we need to support what's called a complemented type lattice. We need this embedded into the top Scala type system as an application, so I don't want to intervene in the compiler. And I need to be able to answer questions about membership and subtypeness. So again, we can represent this such types as ASTs, where we have internal nodes representing the Boolean operations, and then leaf nodes representing the interfaces to the Scala type system, or other special types like signaling types X and the satisfies types wrapping predicates. Here's what the quasi-algebraic data type looks like. We have the combinational operators, the operators that are necessary for the algebra, the special operators for satisfy and equality, and then the interface to the atomic Scala type. I mentioned that the membership predicate needs to always be answerable. So we need to be able to ask a question like, is negative 42 in the type of integers? And we need to get a value of true from that. Or is 7 in the type string or integer? Well, yes. And in given predicates, is 36 in the odd type? Well, the answer is no. That's pretty straightforward, but perhaps a more interesting one is the subtype question, because subtypeness is not always decidable. So if we want to ask, is string a subtype of integer, we can decide that, and we get the answer is no. So we have some false. Is integer a subtype of number? Well, yes, so we get some true. But is odd a subtype of integer? Well, we know that it is, but the Scala system is not able to read our function and figure out what it does in all cases, so it's not able to answer the question of subtypeness there. So the subtype predicate either returns some true, some false, or none, representing yes, no, or don't know. There are many cases, or I guess several cases, when this indeterminism might occur. So obviously in types related to satisfied, there are other situations such as the code itself is incomplete. In order to write a very robust type predicate, it would be extremely compute intensive and have huge code with lots of bugs. So normally the code is written intentionally incomplete, so that sometimes don't know is returned in cases when potentially it could be satisfied. Another problem is that the JVM might load additional types at runtime, so that when the analysis is made, the type may not have a subtype, but later on a subtype gets loaded. So there are limitations regarding the Java system. And then there's some other limitations we'll talk about later with the particular libraries that I'm using in this project. So where are we? So we have wrapped the Scala type system with a more, well, I won't say a more expressive type system, a type system which is able to express some things that the Scala type system is not. It's a simple type system, so it doesn't have a lot of things that the Scala type system has, but it's able to do the type of reasoning that I need to be able to do for these regular type expressions. It supports a complemented type lattice. The Boolean membership predicate, or the membership predicate, is Boolean. It answers yes or no. The subtype predicate is a semi-Boolean, so it might answer I don't know. More information about this can be found in this publication from the 2001 European Lisp Symposium. So challenge 4, how do we assure that the state machines are deterministic? So how do we partition a set of types into disjoint types, especially in the situation where the subtype relation might be unknown? So the problem basically is, given a set of types which might be overlapping, disjoint, inside each other, or sometimes completely coinciding with each other, how do we label the different regions and then colorize those in a way that that all of the regions colored are then disjoint from all the other regions? So this is explained in quite detail in the paper that we mentioned here from the 2023 European Lisp Symposium. Look at some examples with in particular with the Scala system. So if we have a transition, if we have types integer and number, then we need to split those types or decompose those types into what I call the standard partition. So integer and number, integer and not number, not integer and not number, not integer and not number. But what we can easily realize from that is that integer and not number is empty. So every integer is a number, so there's no objects which are integers and not numbers. And then in such a transition then could be eliminated from the finite automaton. And we can decide that unreachability. However, if we look at the case of integer and odd, and we apply the standard partition to that, integer and not odd, not integer and odd, not integer and not odd, and integer and odd, we find out again that not integer and odd is empty. So there's no odd number which is not an integer. However, we can't decide that programmatically. So we have a state in this state machine which is unreachable, yet we can't know that programmatically. The consequence of that is that if you have transitions which are unsatisfiable, such as int and not number, then all of the states that come after that transition in the state machine can potentially be eliminated, unless they're, of course, reachable by some other path. However, if we have such a type as not integer and odd, then the states 1, 2, and 3 are not reachable, yet we can't programmatically assess the fact that they're unreachable. And so this doesn't cause a correctness problem at runtime, though, because given an object such as the string hello, we can easily determine that this string is not in the type not int and odd. So we'll never traverse this transition at runtime. So it doesn't cause incorrectness in the state machine. It just caused unnecessary states which can never be reached. And so the match for the sequence remains of complexity, of linear complexity, despite the fact that we have unreachable states that cannot be detected. Some examples of that in the Scala language. So if we have two final classes, A and B, then we know the intersection of A and B is empty. If they're final, then there's no common subclass, so no object can be both A and B simultaneously. However, if we look at C and D, we have class C and class D, but we don't know if there's an intersection because we don't know if there's some class which inherits from both of these. In this case, G is a subclass of E, a subtype of E, because G extends E with F. So since G is a subtype of E, the intersection is not empty. And E intersect F is also not empty because they have a common parent. There can be an object who is of class E and F simultaneously. So one problem is that if, as I mentioned before, if no subclass exists, well, the JVM might load one later by loading some subclass.jar file. This is problematic. But a more troublesome problem is that beyond Java 8.x, Scala cannot dependably determine the complete list of subclasses. And this is because of a bug in a certain reflections library that's referenced in lots of Stack Overflow and issues on GitHub. Unfortunately, this is no longer maintained. If this guy, Ron Mano, could wake up and fix that bug, but I don't think he's ever going to do it because it hasn't been looked at for many, many years. But because of that, then you can't really make correct subclass decisions after Java 8.x. Finally, I want to look at this problem of the redundant type checks. So imagine that we have these three transitions, number and not int, and not number. We want to be able to take an object such as 3 or such as 12 or such as 5.4 and decide whether we need to move to state 1, 2, or 3. So this more or less looks like this if-then-else code, although it's not if-then-else because it's generated programmatically at runtime. But it's a decision such as this: if some condition, then sum one; otherwise, some condition, sum two; and finally, at the end, if we didn't find a transition, then return none. And as you see, we're checking whether X is an element of type number and not integer. And then again, if it's of type integer, but we've already checked that before. And then on line 8, we again check if it's of type number or not of type number, but we've checked that already before as well. So can we eliminate those redundant checks? So what I proposed is rather than using a static if-then-else structure, we use a decision diagram. So we represent with the green arrow the then branch, and with the red arrow the else branch. And for anyone who is colorblind, the red arrow has this negating dot or negating bubble at the top of it. So follow the bubble for the else case and follow the non-bubble for the then case. So if number and not integer, then sum; else if integer, then sum, etc. So how do we reduce this? It turns out this reduces to a very simple diagram which only contains integer and number check. So how do we make that reduction? So first we duplicate the tree with an extra node at the top checking for number. So we have the same tree on the then branch and the else branch. So we now traverse the then side of the tree and we replace all occurrences of number and all subtypes of number, which includes integer, with stop, which is the everything type. And we traverse the else part of the tree and replace number and all subtypes of number. I think I said that wrong. N and all supertypes of n. So integer is a subtype of number, not a supertype of number. So then what happens is all the instances of number and integer on the else side get replaced with the empty type, and all occurrences of number on the then part get replaced with the everything type as top. Then we do Boolean simplification, interpret the complements of the top and bottom types. And then we can do some logic simplification such as s top and x is x and s empty and x is empty. So these reductions occur. And then every box which only contains s top or s empty can be reduced. So s empty can be replaced with whatever its else branch points to, and s top can be replaced with whatever its then branch points to. So then the tree reduces to much smaller. But then we still have the problem of I. So the tree now only has one occurrence of the number type in there, but multiple occurrences of the integer. So we duplicate the tree again with I at the top node, with the integer check, with the exact same tree on the left and right. But we can traverse the then part, replacing integer and super types of integer with s top, and we traverse the else part, replacing integer and subtypes of integer with s empty. Again, we do logic simplification, and then we replace all of the nodes which are checks of the universal type s top or the empty type as empty, replacing them correspondingly with their then or else branches. So then we find that the whole tree reduces to this simple: if integer, then sum 2, else if number, then sum 1, else sum 3. So the if then else code is replaced with these three branches. And we also notice that we have no branch that returns none, which means that the type check is exhausted. So in summary, we have these 5 challenges that we've looked at: how to represent the RTEs in Scala using an abstract syntax tree, how to construct the DFAs. We didn't actually talk about how the construction went, but we saw a demo of that. A little bit about the problem of representing a type lattice atop the Scala type system, the problem of type partitioning, doing logical manipulation of the types in order to get a set of non-intersecting types which maintain the same union. And then this funny problem of eliminating redundant type checks in the resulting type decisions. As a couple of perspectives, so I have this idea of the open and closed worldview to handle the idea of, do we assume that Java is going to load some other types at runtime? If we know that that's not going to happen because of your particular application, then more restrictive type decisions can be made. As I mentioned before, I'm publishing some of these results in the in Paddle in January. I have a plan to move to Scala 2. I don't know really how much work that's going to be for the very unusual type of code that's in this project. And then there's this big issue of, how do I replace this run mono reflections library? In conclusion, here are the URLs for the different projects. You can look at the Scala code, the Clojure, Python, and the Common Lisp code. I would like to emphasize that I welcome feedback, even critical feedback. I think that science and research can only advance if we're willing to listen to people who disagree with us and improve. And you're free and invited to contact me either at my email address or at Discord. I'm not using other media such as Twitter or Snapchat, whatever all of those things are. So, but feel free to contact me. I welcome your feedback, and thanks for your attention.